name is Paolo Mainardi. I am the co-founder and CTO of SparkFabric. We are an Italian company based in Milan, and we do, of course, a lot of Drupal development, cloud-native custom development, and even cloud infrastructure, mainly based on Kubernetes. We maintain some Drupal modules as well. Maybe the most famous one is Web Profiler. It is a module to help you to have a better understanding on how Drupal works under the hood. And it helps you as well to identify bottlenecks, improvements you can implement at development time. If you still don't use it, I really suggest to give it a try. I am also part of the Linux Foundation Europe in the advisory board. LFE, it's a newborn foundation that started the activities some months ago with the mission, of course, to accelerate the growth of open source in Europe, fostering open source, open standards, and open hardware as well, like RISC-V, and so on and so forth. So I invite you to go on linuxfoundation.eu to know more about the ongoing projects and how you can be involved on the foundation. You can also find me on my personal blog, paolomainardi.com, where I write articles about security, programming, cloud native, and other stuff I find interesting. The last article I published some weeks ago focuses indeed on software supply chain and how modern projects manage dependencies. Spoiler, it's a big mess. Well, before we get started, I invite you all to ask me any questions at the end of the talk. And if the time will not be enough, I will be here till the conference closing. I know we are approaching the ending, but feel free to catch me up. And if you don't have the chance, just write me to the channels you see on the slide, even by mail. All right, let's get started. What are we going to see today in this session? I will start by explaining you what is the software supply chain and why it's so important nowadays to know it more. Then we see the state of PHP ecosystem related to the software supply chain and the threats and the mitigations we can put in place with tools like digital signatures, software attestations, and SBOM, software bill of materials. And finally, I will do a demo letting you see all these tools in actions in a real-life scenario, a simple one, of course. But I think that it's always better to see how the things work. Otherwise, they remain just slides, some theory, and you know. As usual, I did my prayers to the demo gods, and I really hope that the demo will work fine. Let's see. Well, to understand what is the software supply chain, I want to start by this academic definition from Wikipedia, which says that a supply chain is a network of individuals and companies who are involved in creating a product and delivering it to the consumer. It is generic enough that we can use it even for software, from a couple of shoes to a software product of any kind. But of course, we don't have to underestimate the threats and the complexity behind the software supply chain. This is a diagram that comes from the Salsa framework, which is an open source project created by the OpenSSF Foundation, which is the open source security foundation branched by the Linux Foundation, with the aim to deliver the best practices of security in all layers, starting from the supply chain to the software to the infrastructures. This project is not a software framework. Instead, it's just a checklist of best practices that we can gradually adopt to improve the integrity, to improve our, to reduce the tampering risks of our packages, and finally, even improve the security of our cloud infrastructure. The threats are grouped in three main groups: the source threats, the build threats, and finally the dependency threats. Dependencies today are still the main attack vector used by attackers. It's still the weakest point of the chain. It is estimated today that a modern project is composed by an average number of more than 100 dependencies, and then that more than 90% of our code is not written by us. So you can imagine how much we depend on unknown actors in the market and how large the attack surface is just on this side. But of course, attacks can occur at any link of the software supply chain, not just dependencies. And these kind of attacks are increasingly public and disruptive, like SolarWinds, codecov, or Okta. Maybe you heard about them. A very cool thing about Salsa is that for any of these threats you see on this map, you can see a real world example of a high-profile attacks happened recently. For example, in 2021, an attacker gained access to the PHP self-hosted Git server, injecting 2 malicious commits. It was a big mess. And these are the type of examples you will find inside the Salsa framework. Let's now try to imagine the Salsa diagram in action when building a modern Drupal application. We, of course, start by installing Drupal. Then we usually need to install some other Drupal contrib modules, some other composer dependencies, and then, depending on how we build Drupal, maybe we are building something decoupled, we will need a variable amount of JavaScript dependencies. This is very usual. And finally, another bunch of other dependencies may be Python, because we are doing some AI, Go, Rust, or whatever we need to implement our features. On top of that, of course, we have our operating system, which is strictly bound to our application. We need system libraries to compile our PHP extensions, maybe a very specific kernel or some specific binaries or whatever we could need. Then we have usually a CI/CD system with many, many jobs where we do linting, we do QA, we run tests to collect metrics, and so on and so forth. And another very common case is integrating external services to do things on our code base, like, for example, codecov, coveralls, code climate. And this means basically giving full access from the external to our code and maybe more. Then we have to ship our application to our consumer. And our application is on the cloud. Nowadays, we have several options there. We can use AWS, GCP, Azure, or whatever. On the cloud platforms, then we have the freedom to use basically the most desperate services to deploy our application. The sky is the limit in the cloud, like Kubernetes. We can use object storage for storages for our files, some database, Redis, Memcache, Lambda functions, or whatever our stack will need or our dev team will choose. And finally, we have also our local or cloud development environment, because now it's very easy to move our development environment in cloud with tools like Gitpod or DrupalPod. And today it's a very weird agglomerate of external dependencies, the very same of how we build applications. We can extend our editor, for example, VS Code, with the extensions from the marketplace. So if we use VI, we can extend the features of our editor. And this is very common. And you basically have the same risks when you extend your application with external dependencies. It's also very common that we have access to the cloud platform from our development environment, maybe to debug, to see the log, to see the traces, and so on and so forth. As we have already seen in the Salsa diagram, no point in this chain is free of vulnerabilities, especially when the map of services and dependencies is so complex and very interconnected each with another. What we see here is maybe the biggest case in the history of cybersecurity attacks. This was indeed the case which sparked the interest around the software supply chain risks and security. This case happened in 2020 to this company called SolarWinds. They are a major IT company based in the US. And one of their flagship products, called Orion, designed to do network monitoring at large scale for data centers or big enterprises, was compromised by a malware that was then shipped to the all SolarWinds customers as a regular security update. It was later discovered that the compromise was in the SolarWinds build server systems, precisely in the C point of the Salsa diagram, between the source and the build process, where a very sophisticated malware was capable of activating itself and injecting malicious code right before the compilation phase. This attack went undetected basically for months. From that point on, all the new version of Orion contained a malware, basically. This malware was signed by SolarWinds and then shipped to all their unaware customers that were doing the right things, you know. They just enabled the automatic security updates. They checked that the software was signed by SolarWinds, but at the end, they received an upgrade, the update, but with a malware inside. The case was so big because the biggest tech giants like Microsoft, Intel, Cisco were affected, but even the most important national security agencies like the Pentagon, the Homeland Security, the National Nuclear Security, and so on and so forth, but also many, many other important public entities and worldwide national states. The case was so big and concerning that the US Congress invited the CEO of SolarWinds and the president of Microsoft to testify on the case to the Congress to understand why companies that are supposed to protect us from this kind of cyber attacks was instead victims themselves of a long-running and a very large-scale attack like this. Since 2019, as shown in this chart from Sonatype, attacks have increased by more than 700% per year. And there are multiple reasons behind this. First and foremost, it's the massive demand for open source, which therefore means adopting a model made of using many, many third-party dependencies without the right security tools or even the knowledge about the full set of used libraries in modern applications. But even the invention or the improving of new kinds of supply chain attacks, like the typo squatting, dependency confusion, injection of malicious code, and recently even the protestware attacks, that is a very strange attack where the author of a project chooses to sabotage its product to protest against something. There were two big cases in 2022, last year. The color library and the Node APC library, both from the NPM ecosystem, changed their code to become basically a malware, and it was a big mess for all the dependent projects. And this was the case where you depend on maybe the Node APC library, but you don't know that you have this library in your code base because it's a transitive dependencies. Maybe it's a dependency of your dependency. This attack also had a big effect on the global economy. The losing calculated so far are estimated to be around $46 billion, which will increase to more than 80 billion in 2026. And all these reasons together led government to work on cybersecurity laws, new cybersecurity laws. US government started first promulgating the National Cybersecurity Strategy just some months ago. As you see, it's from March 2023, which is a long-term strategy to improve the security posture of all organizations, public and private, and explicitly talking about making software vendors liable for insecure software. This is the first time that a law specifies this kind of liability of companies making software to be liable for insecure software that they ship to the market. The European Commission even worked on a law that is called Cyber Resiliency Act. It's much broader. You will hear about that like the CRA, and you will hear a lot about this in the next few months. The aim of this law is basically to regulate all the products in the market with the digital elements. This means basically that any product capable to run software will be regulated by the Cyber Resiliency Act. And the idea behind this law is basically to create the same CE mark we see in the electronic device also, but specifically designed for software, basically. This law has created a major concern among all the open source communities worldwide because it could risk the sustainability of open source software development in Europe for independent, for foundations, for companies. Because if right now there is a specific exclusion for open source from all obligations that this law contains, it's not very clear the boundaries that who will be liable for. So, if you are interested in this subject and you want to know more about the next actions, the next news about this, you can take a photo of this QR code, or you can just follow the link to subscribe and stay informed about the next things about CRA, that it's a very, very big topic and it will impact the way we build software in Europe, the open source software, in the next few months. The good news is that also the response from the community is very important and full of very interesting stuff. We see here a bunch of logos, products, tools, handbooks, and the new standards or improved ones, specifically designed to improve all the security aspects of open source software and let the companies, professional and public sector to improve their knowledge on this subject. This is a very important topic because most of the times we don't know what is secure, what is not, and which is the right path to follow to secure our systems and to create even a more secure software and infrastructures. So I think that this is a very important milestone because it represents the maturity of the open source communities, and it shows that it's capable to regulate itself without being pushed by just regulations. Well, let's see now the state of PHP ecosystem and how much is affected by all the issues we have seen so far. I want to start by looking at the history of package management in PHP. This is an history that begins in 1999, many years ago, when Stig Becken, I hope the pronunciation is right, wanted to include in PHP something with the goal to provide the reusable components, lead innovation in PHP, providing the best practices for PHP development, and finally educate developers. And the goal was to integrate pair in PHP, and it was the case. And the project, the name PEER stands for PHP Extensions and Application Repository. And it was, for the time, a very, very innovative project. As you can see in this timeline, PHP has been the first of the big mainstream languages to adopt, to create package management stuff inside the runtime itself. Before PHP, there was just Perl. Perl right now, it's not so widely used. And then in 2009, two big milestones happened to the PHP ecosystem. The introduction of namespaces in PHP 5.3 and the creation of the first autoloading standard PSR0 from the PHP Fig group, which is, or was, I don't really understand now. This was a group specifically created to set the interoperability standards between the frameworks. And thanks to these two big innovations, a new and modern package manager was created. It was Composer, of course. I guess most of you know the project, of course, but the question is why? Why a new package manager was even created if we already had the pair? But basically, because pair was invented in another era of computer programming. It was created even before Git. As you can see in this timeline, Git was created in 2005. And all the coding social platforms we now use, we treat as a standard de facto, like GitHub, for example, because, for example, how pair works in how you can publish a module in a new module in pair. It's based on a moderation. It's not like Composer, where you create your Git repo and basically you are all set to publish a new Composer module. And there was even some big technical limitations, like not having a bundle file, like the composer JSON file or the log file to describe all the dependencies and transitive dependencies and make the code base reproducible. And well, trying to add those features to pair would have meant rewriting from scratch. So as we can see from the graphs, Composer quickly became a big success with a broad adoption very fast. Today, it hosts more than 300K of packages, over 3.5 million of revisions, with more than 2 billion installed packages monthly. Yeah, so big numbers. So let's move now on see how Composer works when we install a package. Basically, we start by defining a namespace, like Drupal in this case. Then we define the library name and finally the version. And the namespaces are a strict requirement, and this is a very nice security feature because basically it reduces the risks behind the typo squatting attacks, because basically you have the vendor that you cannot typo squat, and you just have many characters to try to attack these kind of packages. And this is very, very important because, for example, other ecosystem like an NPM allows root packages, which is a big vector of attacks. There is then a public registry, packagist.org, which contains just the metadata of packages. This is a big difference between the other package managers that contains the metadata and the code both. And the code in this case resides always outside in your Git repo, GitHub, GitLab, whatever you have your code. And these features allows to reduce the risks of code tampering, of course, because if you attack Composer or Packagist, and you cannot change the code, but on the other hand, you can change the metadata and maybe to point that package to another repo with malicious code inside. So half and half. And finally, we can have multiple repositories other than the default one. And they are canonical by default, starting from Composer 2. And this means that if a package name is found on a custom or private package repository, only those versions are loaded at all. So we are not affected by an attack known as dependency confusion, where other package managers are hit very hard by this kind of attack. If you're interested on this subject, I suggest you to read this post from the packages maintainers and developers where they explain what are they doing, what already they did to preventing dependency hijacking. Nevertheless, despite all those great Composer security features already in place that we just saw, many supply chain attacks have been conducted against Composer, against Pair too, because it's still a project alive. Someone is still using it. As you can see, just in the last 2 years, we had a lot of very, very dangerous attacks, like 2 critical vulnerabilities on the public packagist.org, which allowed a remote code execution on their server and the open source counterpart. So if you used the project Satis, which is the open source version of packages.org, it's the same software that ran the public service, it was compromised too. And just recently in May, another attack on packages.org was conducted where someone basically had used an inactive account to become maintainer of at least 14 packages. Most of them were also big projects. And, you know, there are many, many type of attacks. So what? Are we doomed? Where should we start to improve our security practices, being more resilient, to detect before then they happen, this kind of stuff? I guess that the first step we have to do is to look at our application and all its dependencies, including the operating system, as a single unit of code. How we can achieve that? We can use some industry standard like OCI containers, so we don't have to reinvent the wheel. They are better known as Docker containers, maybe. They allow us to do very nice things like defining our application and all the system dependencies in a reproducible way just by using a Docker file. As a result, this container image can be moved between the clouds, between our local development environment to the clouds, and so on and so forth. And finally, we can also rely on the big investments that the cloud native ecosystem have now. Because, for example, we can create, reuse the most modern cloud native tooling, like the tools to generate SBOM, the tools to do digital signatures on our containers, and so on and so forth. Containers today are also very useful when we are developing our solution with tools that you are maybe just using, like DDev or Drupal pod or Dev containers and such. Basically, containers today are everywhere, and they are very easy to use. And let's see now what is the OCI acronym that I just mentioned, and what are the OCI images and how they work. OCI stands for Open Container Initiative. It is a set of standards to define standards around containers technologies such as runtime, image, and distribution. And basically, an OCI container, an OCI registry can even store any kind of artifacts, not just containers. And this is a very important feature that we'll see later why it's so important. So the question now is how an OCI container can help us to improve the trust between us and the digital artifact of any kind. How I can be sure that what I'm running is coming from a trusted source. Basically, this is the same question that Ken Thompson posed in 1984 in his famous paper, Reflections on Trusting Trust. And the answer was that we cannot really trust the code we don't totally write ourselves, basically. Instead, we should put more trust on the people who write it. So, to higher the bar of trust, we need to know at least who built it, when, how, and we can do that using things like digital signatures and provenance attestations. And finally, we need to have a way to produce the list of things who made the artifact, which is basically the list of ingredients that are the composition of the artifacts that we are going to consume or to release to the market. So using digital signatures with the key pairs, the famous public and private keys that we can use maybe with SSH, it's the most famous case, they can ensure integrity, authenticity, and the no repudiation, which are the three key elements to having or giving trust. With integrity, we ensure that the data was not altered along the way. Authenticity, that the data was sent by the signer, the developer or the companies, no matter. And the repudiation means that the designer cannot never deny the authenticity of the signature. They can just say, I'm sorry, I lost my private keys. Someone signed this artifact for me. But existing tooling, like GPG, are very, very complex to use. Have you ever tried to use GPG and the hellish list of arguments? It's basically a mess. Trust me, it's not very funny, but there are also other big problems in the key management itself, because managing keys is so hard. We have to distribute our public keys to our key to our users. We need to keep our private key in a very secure storage, and if compromised or when, we have to manually inform all the users involved that I'm sorry, my keys was compromised, this is my new key, and so on and so forth. And then even retire from the market all the software that previously was signed with that key. So you can understand how hard this can be when you have thousands of customers, basically. This is why digital signatures today are not so widely used in software, even though they have in open source software, even though they have existed for decades, basically. However, there is a new project called Sigstore, which is an ecosystem of projects, basically, with the aim to resolve all those issues with digital signatures, and not only that. Sigstore has a very fast-growing community. It's a project created by the sponsored by the OpenSSF Foundation. And the community is growing very fast. It's already mainstream adopted by projects like Kubernetes and many, many other big vendors. GitHub is integrating, or it's just integrated in their package management features. And other ecosystems are working to integrate it, like Ruby, Gem, Arch Linux, and so on and so forth. So the success of Sigstore is mostly driven by its very innovative features, like the keyless signing. This is very, very important. It works by using basically your public identity, like GitHub, Google, or whatever OpenID provider supported by Sigstore, to generate a short-lived certificate and use it to sign it on your behalf. Actually, this feature completely removed the burden of managing key pairs because they don't even exist in this scenario. You don't need any kind of keys. You just need to trade your public identity to generate this very short-lived certificate and sign with it. And it's all managed by Sigstore. The other important features are that signatures metadata are stored in a tamper-resistant public log, which is publicly accessible even by API, allowing everyone to verify who signed what and when. So if you think that you are compromised, you can always look at this registry and see what is signed by whom. And finally, the signatures are stored alongside images in the OCI registry. This was the important feature I mentioned at the beginning. So you don't have to worry about to find a new dedicated storage for your signatures, basically. The other key element in the supply chain are the software bill of materials, known as SBOM. They represent the list of ingredients who made the artifact, basically. You can use it to do things like vulnerability scanning, license policy, find abandoned dependencies, and so on and so forth. But of course, generating SBOM today, it's a very complex problem because dependencies live at different layers and they are managed by way different package managers. From the operating system to the programming languages, they basically package and they have versioning numbers or versioning scheme very, very different in one with another. And so, of course, we have even the static binaries like Go, Rust, etc. that are statically compiled, but they have dependencies as well. So there are some tools that can really simplify this job. I mentioned here the most biggest one, like Syft, like Aquatrivi, and recently even the Docker command line has a new command, which is Docker SBOM, to allow you to just giving your image as an input and having back your SBOM automatically generated by this tool. Well, finally, the demo time. Sorry if I bothered you with all this information. We are going to see mainly three things here. How to sign a container image using Sigstore and Cosign, which is the software of the Sigstore ecosystem. How to generate and attach a software bill of material to a container, and how to push it in a registry, exactly as we do with the signatures. And finally, how to use the generated SBOM to scan for known vulnerabilities that we already have on our Docker image. And to demonstrate all this stuff, I will deploy the container on a local Kubernetes cluster, which has some security policies running that will allow me only to deploy containers with the signatures signed by me and with an SBOM attached. I'm not going, of course, in any detail about the Kubernetes cluster. It's off topic, but you can find with this QR code in my GitHub repo with all the code that allows you to reproduce yourself this demo. All right, let's move on the terminal. Okay, so this is our Docker file. Basically, we are starting, we are using the base image from Drupal, the official one, 10.09, PHP 8.1, and we use Alpine because we want a very small image. We don't need the big Debian or Ubuntu stuff. Then we install a JavaScript dependency, just one basically, but to install it, of course, we need the Node.js runtime and NPM. And finally, we installed some Drupal dependencies. In a real-life scenario, I will have used, of course, a composer.json file, but for the demo's sake, it's good. So what we are going to do now is to build this image, push it to a registry, Docker build. Well, and now when we have our container, and when we can try to apply this Docker image to deploy this Docker image in our Kubernetes cluster. And what we expect that our cluster is basically saying that it can admit just images with an SBOM attached and just images with images signed by me. So we can start by using the Sigstore project, which is called cosign, and it takes as an input the image with the tag. Okay. And now it will start the keyless signing process that I was mentioned before. Basically, now I'm logging on Sigstore with my GitHub account, and this is it. We don't need anything more to have our image signed by us, basically. We can check where this signature was stored. And as we can see with the crane, basically we queried the Docker registry, the container registry, asking all the tags for this image. And as you can see, a new tag has been created with the content of our signature. This is a standard, and other tools are capable to understand what is this hash. And with cosign, we even verify these signatures, of course. We can see it. Okay, it's missing the tag. And as we can see here, basically, we can see that the issuer was the GitHub login OAuth, and the subject was me, basically. And now that we have our image and we have our signatures, we can try again to apply our container on our Kubernetes cluster. And now we expect that our Kubernetes cluster says that, okay, now we have your signatures, but I need even, as by the policy you defined, even an image with its SBOM. To generate this SBOM, I use Syft. And Syft takes as an input the image and the tag, and will parse this image layer by layer, and finally will extract all the packages inside these containers, including all the composer and node dependencies and even the operating system ones. Okay. Okay. No. And as we can see here, we have a big number of packages. We have more than 980 packages just by installing basically one node dependency and 4 composer dependencies. And we even started by Alpine, which is a very, very small Docker image. And the output of this tool can produce the SBOM in different formats. This is the human readable one. You have the name, you have the version, and you have the type to understand where this dependency comes from. And you can see that most of the dependencies are coming from Node. We have some PHP composer dependencies as well, and the APK are the Alpine ones. So now we need a version, a machine-readable version of this SBOM, and we just pass as an input the image with the tag. We say that we want the format cyclone.dx JSON. There are many formats that we can use to produce machine-readable SBOM. There are 2 compelling standards now. One is cyclone.dx, the other one SPDX. I'm just using cyclone.dx for no specific reasons. And we can save the file. And finally, I let you see what is inside. There are many, many more information than the table we just saw, of course. Well, for example, we can look at a Drupal package, in this case, the meta tag package. We can see the version, we can see the license, we can see its URL, which is a standard. And then we have all the metadata information about how the tool found the package and where it's located inside the container. And then we can see maybe another type of package. This is from Node, where we can see even the author. This is money information that Syft cannot extract from composer packages. I don't know why. We have the name, we have the version, we have the license, and so on and so forth. So now that we have our SBOM, we can always use cosine. We use a new command, which is a test to attach files to our container. And we basically say that we want to attach our SBOM file. We say that this kind of predicate is a cyclone.dx type file. And we just pass as an input the image and the tag. Cyclone.dx, no, okay, cyclone.dx, okay. And we are basically doing the same procedure we did for the signatures, because this file will be signed by us and will be uploaded on the container registry that will contain at the end our container image, our signatures, and our SBOM signed. We can check the registry again, and we see that now we have 3 stuff, basically our container image, 100, our signatures, and our software attestation with the SBOM attached. And now I can try again to apply our Kubernetes deployment. And now I hope that everything is working fine. And this is, of course, a very simple example of the things you can do using this kind of tools. Basically, I could define a policy, for example, to say that you cannot deploy nothing with a critical vulnerability. And talking about this, we can use another tool once we have the SBOM file to pass all the dependencies with the versions that are known, and download the CVE database with known vulnerabilities and understand in this scenario which kind of vulnerabilities we already have. As you can see here, we started by an official image. We just installed 1 node dependency, 4 composer dependencies, and we are just affected by 2 critical vulnerabilities, 2 high, 11 medium, and so on and so forth. And you have the list of the package, if the vulnerability is fixed or not, and so on and so forth. Of course, those information cannot be always applied to all scenario, because maybe you are deploying something that I have a library affected by a vulnerability that cannot be exploited, but you know, those are the informations that we should always have when we build a new application. Okay, and now we can go back to the slides. Okay, so with our takeaways, basically OCI containers can help us to simplify how we package our software, how we ship it, and how we can rely on the modern cloud-native tooling where all the investments are going now to have all this kind of information basically for free. It's quite simple to use these tools, like signing the artifact with Sigstore. It's very nice and easy, and remove basically all the burden of managing key pairs, and because they don't even exist, and they are stored alongside our OCI image. You saw how easy it was signing something. Then we should automatically generate the SBOM file with all our dependencies using tools like Docker SBOM or Syft, or you choose it. And once we have our list of ingredients, we can do a lot of stuff. Basically, we saw that we scan for non-vulnerabilities, but for example, we can scan as well for licenses. Maybe we are producing something that does not allow to have, I don't know, the GPL license or the BSD license, so we can have all this kind of information for free. Another important point that we didn't see in this demo, but I really suggest to implement because it's quite easy as well. It's to automate your dependencies using tools like Dependabot if you are on GitHub, or another open source tool which is very powerful, which is RenovateBot. And those kind of tools basically help you to automatically update your dependencies, open PR or MR, and automatically with some policies to merge them, so you don't have any kind of friction to use it. And finally, another very nice addition to Drupal is the Drupal security advisories for Composer, which is basically a composer library, which once installed, it downloads the security advisory from Drupal, the database, and will start to inform you when you are using something with known vulnerabilities of any installed packages or the packages you already have in your code base. Well, that's it. Thank you for your attention. I don't think we have any time for the questions because we are 5:02. Anyway, there is a question there.
Hello. Thanks for your talk. It was very interesting. I wonder whether there's also a way to check the code is authentic. Like, I don't know, maybe there's some unwanted patch applied somewhere and like the code base changes afterwards.
Yeah, to detect that, the signatures are capable to do that because basically when you create a signature, so you created using doing a checksum on your code base. So you can try to reapply to recreate this checksum. If they are different, something changed. So you are using tempered code. This is why digital signatures must be always used. Okay, thank you very much.
Thank you.
Hi.
So I understand the concept.
Yeah.
Now, containers, okay,
Yeah.
DDEV are great, I think, for local development on local machines, sort of
Yeah.
that stuff. But if I've got a server, not a cloud server, but a proper server, does it overcomplicate things if I have a container on that server?
Why? Which kind of issues?
Because I've never on a remote server, I've never used a container before. I've just used the stuff from my container and sent it up there.
Yeah, yeah.
That's what I've just used.
Yeah, I'm using the dev, of course, for development. When we ship the applications on servers and use tools like Kubernetes, for example, then you don't need it because you can just do a Docker run of your container on the server. But which are the issues you have found?
Would it?
Let
Okay.
me bring the.
Just on this program. Okay, then you might do it. Yeah. Probably better with your The team doesn't always fit. Right, awesome.